So, in this, the amplitude modulation, part 5, what up to part 4, we have generated the amplitude modulated wave. When we have transmitted the amplitude modulated wave, now at the receiver side, we have to reconstruct that message signal. So, for that, what we require is the envelope detector. For the amplitude modulation full carrier wave, we are using envelope detector to reconstruct at the receiver side. The process of demodulation is used to recover the original modulating wave from the incoming modulated wave. So one of the method to demodulate the AM wave is the envelope detector. It consists of the diode, resistance, capacitor, filter, and the figure for that is defined over here. So what we have is a AM wave, then we have RF, the resistance, then we have this diode over here, and we have used this R and the load resistance. So what we have is an envelope detector circuit diagram in which the diode is assumed as the ideal. It has a constant resistance RF when forward bias and infinite resistance when it is reverse bias. The figure over here is a sinusoidal AM wave with 50% modulation. This is how the wave will look where wave will look like. Now look at this, the envelope detector. The problem with this wave is the envelope detector, which is the defined over here, has some ripples. Ripples is it should basically smooth, but it is not smooth. It has some ripples in it, and which is not required. So these ripples, which are unwanted part, can be removed using a low pass filter. Now we move to the circuit diagram over here, which has the diodes, which is ideal, and how it will work, that is defined over here. So when we are having a positive half cycle of the input signal, the diode will be forward bias, and the capacitor, that is C over here, will be charged to the peak value. Whenever the diode is forward biased, this capacitor is charged to the full value of the input signal, and when the input falls below this value, the diode becomes reverse bias, and the capacitor is charged discharges through the load resistance RL, and the discharging process continue until the positive half cycle. So when the input signal becomes greater than the voltage across the capacitor, the diode again conducts and the process remitted. So what we have done is, whenever it is a forward bias, this will charge to the maximum value. So, and whenever the voltage over here falls below, put this diode in the reverse bias, that will discharges through it. So what we have done is, we have used the diagram in the next page over here, how we can use the RC time constant in the envelope detector. So whenever we are having the time constant RC, that is combination of the resistance and the capacitor in the previous circuit that we have defined. So time constant equals to RC, and whenever this value is too short, then we have this envelope like this. So it will not be able to follow this on. So, and whenever we are having a time constant RC that is too long, then the wave will behave like this. So this is the total what we have. This is the charging time. This is your discharging time. This is your charging time. This is discharge. So whenever we are having the RC too long, then it will not be able to follow this envelope. The discharging time will be too much, and it will not, ideally it should follow this envelope. Likewise over here. So whenever we have too short, again it is not following the envelope. Whenever it is too high, it is again not following the envelope. So using the various diagrams and the figure, or looking at this, the critical value that should be used of the RC time constant, that is 2 by B, it should be less than 1 by RC. This is the time constant, and it should be less than 2 pi FC. This B is the bandwidth of the modulating signal or the message signal that we transmit. So using this design criteria, we should keep the values like this. Otherwise, we will not be able to follow the envelope of the modulating signal, and by this, we will be not be able to reconstruct the signal at the receiving end. Thank you very much.